Hello, we are looking at our first question here, and based on momentum, the conservation of momentum, we've got our masses and we've got some details about velocity. So remember, the formula is mass times velocity, and you'll do an initial and a final stage for that. So this is May and June 2022 mechanics paper. So drawing our little sketch as always, mass and velocity, and we see for B we are at rest, so we have no velocity. So the initial stage now for our momentum is 5 times 8.5, 3 times 0 is B, so 42.5. And now we've got a second part, so we know that A is a quarter of the speed of B after the collision. So of course that means like 1/4 of V if B is equal to V. So same details of course, just changing those velocity aspects. So 1/4 of V, so 5 times 1/4 of V is equal to 3V. And equating that all together, 42.5 is equal to 17 over 4 V, and so V is equal to 10 meters per second. So that was the speed of B after the collision. Part B, find the loss of kinetic energy of the system due to the collision. So our formula for kinetic energy is mv squared over 2, or 1/2 mv squared. So that's our part A, just the initial one that we just had, and the answer was 180.625. Now the final is going to include A and B. So A this time, our velocity has changed to 2.5. It's 1/4 of V, if you look just at the top there. And for B, it's 10, of course. So to take note of those details, that was for A and B, and our answer is 165.625. And so the loss is, subtract them, you'll get 15 joules. That was part B. So we're given some coplanar forces with certain magnitudes, and we have to find the magnitude and the direction of the resultant force. So I'm just putting down here our components for up or down. So the force going up or down, you have 16 sine 50 plus the 20 sine 60, and it's equal to our force going up, that's 60. So get your calculator out and you'll get 30.42 ... So horizontally, resolving our forces horizontally, we've got the 14 newtons plus a component of 16 cosine 50 is equal to 20 cosine 60 on the other side. So that's 14.28 ... Now, we want to find the magnitude, and this uses a Pythagorean trick here. So we have our sine and cosine, our opposite and adjacent, if you want to look at the trigonometric aspect of it. So using sine and cosine here and squaring them, you get 33.6 newtons. So that's the magnitude of the resultant force. You can draw a triangle there as well if you want to make it extra clearer. Our angle, our direction, we find this way. So tan, of course, is opposite over adjacent. And we kind of know, well, you can kind of guess where you can see the yellow line there. You can kind of guess where we're going with this. In terms of the strength, or in terms of where the force may be more prevalent. So it's going up into the left-hand corner at about 65 degrees. So you have to make sure you look at this in a certain light. It's about 65 degrees up from the 14 Newton force, so in the negative x-axis. You could describe it in different ways. You could say it's, in terms of bearings there, you could say it's like 335 degrees in that direction, so on the negative x-axis, just up from that force that you see is 14 newtons. And always just write out the little bits there if you can, so 65 or 64.8, up from 14 newtons in negative x-axis. In question 3, we're dealing with a tension in the string. So let's draw our little sketch first. We have two particles A and B. A is 2.4 kilograms, so 2.4 G, and B is 1.2 G. And we have tensions in them, we'll draw in a second. We have a light, inextensible string as usual, and it's smooth. And we have distances, we'll deal with that in a moment as well. Released from rest, and so A reaches the plane and does not rebound, and B does not reach the pulley. Okay, so show the tension in the string. So we usually do this. Just think to yourself which one is bigger. So 2.4 times G minus T is equal to 2.4A. So F equals MA is our formula here. And then T minus 1.2 G, or 12, is equal to 1.2A. I'll keep that consistent there. So that's a whole system. You can put it together. T and T, so tensions cancel out. You'll get minus 12 is equal to 3.6 A. And so A is 3.33, so 10 over 3 is the accurate answer, meters per second per second. From there, we'll sub that back in. So we can substitute that value back into one of our formula or equation. And we'll get T is equal to 16 newtons. So we found the tension in the string and the magnitude of the acceleration before A reached the plane. Part B. Find the greatest height of B above the plane. Okay, we're going to have to draw another little sketch here, I think, because we have distances we were given. So we were given 2.1 and 1.5. And we'll have to find another vertical height. So if we just start from the ground up in a way, you'd have the 1.5 to A, and then 2.1 meters to B, and from there we're not really sure, so there's a maximum height we have to find, and we have to find that little distance and add them all together basically. So we need to find we have to use suvat. Okay, so I need to find my velocity. So equating, of course, potential energy and kinetic energy, I need to find the velocity of B. So V squared equals U squared plus 2AS. We'll get that there. Those are those details for B. So V is equal to V squared equals 14. So V equals root 14. And then we can do our energy transfer. So we can find our height. You can rearrange that formula as well. So 1/2 mv squared equals mgh. You could rearrange that, like you could cancel out the masses and get h is equal to v squared over 2g. Just depends on what way you want to do it. And we have our 3 bits there. We can add them together and we get 4.3 meters as our final answer for the greatest height of B above the plane. So we're dealing with particle A along a horizontal track. So we draw that there. We have a velocity of 8. It passes a point. And there's 4 seconds in between there. So there's another particle B that at 4 seconds their velocity is 20, and it also has a deceleration of 2, so -2 for the acceleration. And b comes to rest when it returns to the origin. So find some expressions in terms of t for these, a and b. Okay, so a is t plus 4. So just using SUVAT formulas, I suppose, you get s is equal to 8 times t plus 4. So 8t plus 32. That's the first one. Second one for b, we have u is 20. So 20t minus half at squared. And just simplify that there. Half times 2 is 1, of course. That's that. Those two parts there. We found our expressions in terms of t. Part b. Find the values of t when the particles are the same distance. So if they're the same distance, then you would equate them, they're equal. So making them equal, we can then solve for some equation. We've got a quadratic here, so we can simplify that again by dividing by 4. So you get t is equal to 4 and t is equal to 8. So the values of t when they were the same distance from the origin was at 4 seconds and 8 seconds. Third part, or part C, we've just sketched the displacement time graph. So we're dealing with a straight line, at plus 32, and a quadratic, negative quadratic, so be careful there. So just kind of draw that out, and you have to do a sketch anyway, but find out the little bits and pieces in between. So I've put in there our time of 4 and 8. I've put in the y-intercept for our straight line, which is 32, and you want to also maybe just look at like what happens at 10 seconds, what happens at 20 seconds for each equation. So just checking these little details. So we can see for straight line at 20 seconds, we went to 192 meters. So I can put in the full line there. And we've quadratic and negative quadratic, so it's like an N shape. The vertex is at 10, it goes to 20, so it's kind of going over a little bit there. My picture won't be brilliant, but just it's an approximate there. At least I know the details are correct. So have those details in there at 4, 8 seconds, have your y-intercept of 32, and it should look more or less like that. When you're drawing by hand, it's a lot easier. A block of mass 12 kilograms is placed on a plane. It's inclined at an angle of 24, so let's put in our little forces here. We have an angle of 36 as well on the horizontal there, above a line of greatest slope. Tension 65, and we have to find mu, which is going down, is an opposing force. And I have all the details there basically. So we're solving our forces here. So parallel plus F. So F is equal to 3.77. And then our force perpendicular to that, and we'll include or there, so put in or, our contact force. So just remember we're doing it perpendicular to the parallel part there, which of course is opposite. And so or is 71.419. So you know your formula is F is equal to mu or. You can rearrange that, so mu is equal to F over R. So 3.77 divided by 71.419. And you're going to find the value of mu is equal to 0.0529. A car of mass 900 kilograms is moving up a hill at incline 0.12. We just put in our details on our diagram here. So we have an initial speed of 11 and a final speed, or speed up the hill anyway, of 16. And we have a distance, we'll deal with that in a second. And we've also been given a power of 24,000 watts. So just set up the diagram here. We're going to have a component force as well. So after 12 seconds, the car traveled 150 meters as well. We'll do our energy calculations here. So kinetic energy, mv squared over 2. So we'll do both our initial and final velocities there. We get 60,750. The potential energy, 900 times gravity times, we don't have our vertical height above the ground here, so 150 times 0.12, and we get 162,000. Remember, the power is work done over time, so just putting those details in, we get 24,000 times 12, which is 288,000. So 288,000 minus our 60,750 and minus our 162,000, and we should get our answer there. So 65,250 joules. So the car then goes along a horizontal road. There's a resistance of 1,520 plus 4V newtons. Our power is 32,000 watts. And we don't know the velocity, so we have to find our speed and velocity there. So keep in mind that the driving force is our resistance to the motion of the car. And of course, driving force is power over speed, based on your equation or your formula. So dF equals 32,000 V. So 1,520 plus 4V is equal to 32,000 divided by V. You can plug that all together. So V times the left-hand side, you get 4V squared plus 1,520 V minus 32,000 equals 0. Just move that 32,000 over. Divide by 4 and you'll get then a simplified version of that. And so we'll get two answers for this. Only one of them will be relevant. So V is equal to minus 400 and V is equal to 20. So of course our relevant answer is V is equal to 20 meters per second. And that's the speed that the car was going at. In our last question on this paper, we have now two equations for velocity, and we're given a range of time as well. And we're going to put our little mnemonic device on the right hand side there for variable acceleration. So from displacement to velocity to acceleration, we want to show that there is an instantaneous change in the acceleration. So we're going to find that acceleration now through derivatives, deriving it using differentiation. So 0.5 is our first part. So that's our first acceleration. So will the next part be different? So the acceleration of this one is 0.5 t minus 8. So plug in the value of t, which is 10 at that point. 0.5 times 10 minus 8 gives a minus number, so minus 3. So we've just shown that the acceleration has changed at t equals 10. Between our line and our quadratic. So finding next the total distance. So again, go back to that mnemonic if you want. I think we'll be integrating. So have a think about it for this part. It could be clear cut. It could be clean from like 0 to 10, from 10 to 20 as we have it given in the question. But we want to check this. So we want to check our roots. Does it pass through the x-axis or anything like that? So I'm going to do that now. So our second equation is a quadratic. I'm going to use the quadratic formula to see if we have any points where it passes the x-axis. And from there, we'll get 12 and 20. So 20 is perhaps obvious. So we do have a change at 12 seconds. So we know it's a quadratic, we know it's going to go down there somewhere and then to 20. So we know it passed through 20 if you want there, but that should make sense, more or less. Your picture is just a sketch, remember. Just demonstrating that you understand. So we just integrate our two equations now. So our first one will be straightforward, straight line. We'll just plug in a value for that one at 10 seconds. Our second equation, we're going to have to do two stages, as I said, and you can see in the graph over there. So there's going to be two stages for this. We're going to do it between 10 and 12 seconds and 12 and 20 seconds. So they'll be our bounds as well at the x-axis. So there's our two answers there. There's our integrated form. The integrals. Just put little ovals around them. Why not? Our next part, so we're going to actually plug in the boundaries then. So between 0 and 10 seconds, and then we have between 10 and 12 seconds, and lastly, third stage is between 12 and 20 seconds. So our first one 0.25 and then 10 squared, which is 25. You could do that with the area of a triangle calculation as well, as you can see. So for our next two parts, we're integrating the curves above and below the x-axis there. So 0.25 over 3 is 1 over 12. Let's just simplify that there. For myself or for yourself, for both. So the boundary of 12 and then 10. So essentially I'm doing the same thing here, and I'll be doing the same thing for the next one as well, just plugging in 20 into our integral minus 12, replacing t. And I've just done a kind of a composite calculation here for that. So putting in from 10 to 20, the total answer is 26 seconds. Meters. So 26 meters plus 25 meters will be our final answer. So S is 51 meters. That's the total distance covered by P in the interval, and our sketch on the right hand side demonstrates that perfectly as well.